Okay, let's start. So in the last class we started to look at the noise, and we essentially saw that all lossy elements, they generally tend to have thermal noise, and for a resistor we have this thermal noise, and that typically is modeled, let us say, by a parallel current source. So this will have a flat power spectral density with a value 4 kT by R. If it's a voltage, it's 4 kT times R. Similarly, for a MOSFET, once again the drain current will have thermal noise, and to model this we again say that we have a noiseless transistor, but the noise is added by a hypothetical current source, and the power spectral density of this current source is 4 kT gamma times Gm. And in addition, for a MOSFET there was also flicker noise that is also modeled like a parallel current source, and the power spectral density of this guy is actually inversely proportional to the frequency. Okay. And as I mentioned, thermal noise is something fundamental that is coming straight from thermodynamics because of thermal energy, whereas flicker noise is process dependent. Okay. So and then we also saw that if we have all these noisy elements in a circuit, let's say something, it has all the noisy elements, say a lot of transistors, resistors, etc. Now here if I go and apply the input, make some space maybe. Yeah. So if you go and excite this network with a small signal input here, so ideally if you look at the output, either the open circuit voltage, or let's say I'm interested in the short circuit current here, the output current here will obviously have contribution due to the input, but you'll also have noise. And one nice thing is the input we apply is a small signal, and noise amplitude is also really small. So both of them are small signals, so you can take this nonlinear network and linearize it using small signal approximation. So once it is linear, to find the contribution only due to the noise, we can say that the input is 0, and whatever you get here is only due to the noise. And you also saw how you go about doing that. You take each noise source in the network one at a time. So say you take the kth noise source, say it has a voltage power spectral density SVK of f. You find the transfer function from that noise source to the output, and let us say that has some transfer function, or let's say start with the current here. So let us say we model it using current source, so it's say SIK of f, and then you find the transfer function from that current to the output current. So that is some mod h of f square, like hk of f, and then you sum it up for all the noise sources. Okay. And you do this because the noise sources inside the network, they are all uncorrelated, so you can directly add their power spectral densities. Right. So this way you can compute the noise at the in the current, voltage, anything. This is nice, but as we saw in practice, we don't want to just compute the noise, but we also want to be able to say if we have two networks, which among the two is more noisier. And in that context, just looking at the output noise is not painting the full picture, because as I mentioned in the last class, let us say you take the same network, at the output you have a gain stage or an attenuator stage. It will look like here the noise is higher, here the noise is lower. So that is not painting the true picture. So that is why instead of looking at the noise at the output, we tend to model the noise at the input. So what we did was this: we took the same guy. So to model this, we told that the network here is noiseless. The noise is coming due to an equivalent voltage source. Vn in, right? But this is nice as long as you don't have any source resistance here. But as you know, the input that will be exciting the network will have a source resistance which is not under your control, and it is not known before. So if you have a source resistance here like this, so in the model also you'll have the same guy. Oops. So now we have a problem, because here it looks like not this entire it looks like this entire noise voltage is not exciting the network. That seems to be getting divided between RS and the input impedance. And in a case where the input impedance is very small, or if RS is very large, it looks like, let's say you take a case where RS tends to infinity, then this is not there. It appears as though nothing excites the network and the noise here is 0, but that is not the case. And that was happening because of the inadequacies in this model. So to rectify this, in addition to the voltage, we also added a current. So I'll call it IN. Right? So this both the current source and the voltage source together, they capture the noise generated in the network, and this is a convenient way to model the noise. Right? And it's also easy to see how to compute these two. So let us say you want to find out VNN and INN. What you do is the following. So from here, for what value of RS do you think the noise will come only due to the voltage source? RS is 0, because if I make RS 0, this entire voltage is put in parallel to the network. That is going to completely excite the network. The noise current source will simply flow into the voltage and nothing will go into the network. So this is something you can do. You RS 0 meaning you short the input, right? So if you short the input, then you first find in our network what is the path spectral density in the output current or voltage, whatever. And here, what is the noise path spectral density in the current? They call it I out. What is the S I out of F here? Yeah, it is basically the I'll write it here. This is the path spectral density of this guy times the transfer function we'll have from here to the current, and that will have a dimensions of admittance. So times F square, and these two have to be equal. So equate the two, so then you directly get SVNN of F to be S I out of F by mod Y of F square. Okay. So you find the short circuit current or the voltage, find the noise in the short circuit current or the open circuit voltage in your actual noisy network, divided by the appropriate transfer function, and that gives you the input referred noise. Right. So similarly, you can also repeat it to find the current, the input referred noise current. Yeah. So here, what should I do to RS to make sure that if all the noise is coming only due to the current? What should I do to RS? Infinite. So I'll open this now. Now if I do this, I'll find some S I out of F. Again, that need not be same as what you had here. That could be something different. So maybe I'll call it S tilde or something. So you open RS and then you find what is the short circuit noise current, and then you take this model. So here, what is the noise you will have in the current? You will have the current, you will have noise only due to this input referred noise current. So path spectral density of this fellow times the transfer function from this current to the output current. So that is going to be a transfer function, a dimensionless transfer function h of f. So then you can directly write it. The current will be so here I computed the noise in the short circuit current. You can as well compute the noise in the open circuit voltage. Whatever you get for the input referred noise, voltage and current will be same in both cases. Okay. Right. So let's look at few examples so that you get used to it. So please work with me so that you get a hang of this. So this vocal, at least to some extent it makes clear, it makes sense. Let's look at few examples. And as usual, we'll start with single transistor stages, common source, common gate, etc. And then we'll go to better ones. So let's start with common source, and before going that, just one observation. So here you see that if Rs is 0, if Rs is 0, or if the input resistance here is infinite, then you just need voltage, right? You don't need the current at all, because if the input impedance is large, the entire voltage source is going to drop across the network, and similarly if the input impedance is infinite, none of this current will enter the network. So the noise will be completely coming only due to the voltage source. So that is something you can observe here. Let me mark it. If let us say the input impedance is infinity, to model the noise you need what? Only voltage is enough. So which means if you actually go ahead and compute IN in, you will find that this will be equal to 0. Okay. So then let's look at an example, a few examples, so that you get to know how this is done. So as usual, let's start with common source. Common source here is where I apply the input. This is my output port and supply. And for noise calculations, for the most part, we'll assume R0 to be infinity so that we can get a quick and dirty estimate. So now again, here you see that the input is to the gate. If I ignore the gate capacitance, what can you say about the input impedance? Infinite. To model the noise, I just need voltage, right? So we'll only find the voltage. So again, to find the voltage, so okay, so let me draw this here. So what we are essentially trying to do is model this noise here using this fellow. Everything here is noiseless, and the noise is coming due to an effective current and a voltage. And you guys know, since the input impedance is infinity, only the noise voltage is enough for this guy. And to find the noise voltage, what should I do to the input side? Rs is 0, so which means I'll go and short it. So let me actually keep the circuit here and short it. It's all small signal, so incremental circuit is what I'll draw quickly. So input is shorted. Here also it's shorted. Let me demarcate these two. Fine. So again, you can either find the open circuit voltages here or the short circuit currents. So typically finding currents are easier in some cases, so let's do with short circuit current. Right. So again here, if I call this RD, how many noise sources are there in the network? I mean, resistor is there and MOSFET is there, right? So to model the noise due to each of them, let's start with resistor. So let us say model this guy with a noise current IN. I mean, remember that the polarity of the current doesn't matter, because finally we are taking the power spectral density, so goes off. So if this is the noise current here, what is the short circuit current? Yeah, so I out will be same as your, so you mark it clearly, this is I out. So due to the resistor, I will get the entire noise current at the output. So similarly, if I take for the MOSFET also parallel to the drain to source, I have a current, let us say INM. So what can you say about this current? That will also directly flow into the short circuit, right? So this is going to be just fine. So if I find the power spectral density, what is that? What is the power spectral density of the resistor's noise current? It's 4 kT by RD. I mean, the output short circuit current is sum of these two currents. So power spectral density will be sum of the two power spectral densities. Again, that is because the two noise sources are uncorrelated. So I can directly add their powers. So this is the power spectral density in the resistor's noise current. For the transistors, it is 4 kT gamma times Gm. Okay. So here we have found this So next we have to find the same thing in our noise model. So here if I call this as I out here, I just need to find the transfer function from this voltage noise to the short circuit current. And what do you think the transfer function is? Basically, if I were to find I out, okay, it's minus GM. GMR, no, it's just GM. Is that okay? I mean, here the idea is this is a model wherein these two guys are noiseless. The noise is modeled only by these two fellows, right? To find the voltage noise alone, we are making RS to be 0. So at the gate, the voltage is VN in. The small signal current is whatever minus GM times VN in. So that entirely flows to the output. Again, the minus doesn't matter because we'll take the magnitude squared. So the transfer function here is GM. Okay. Oops. So then if I try to find the input referred noise voltage power spectral density, how will I find it? Basically divide this guy by magnitude squared of that. So if I do that, I'll get I think I'll get 4 kT by, let us say, I'll take GM 1 by GM RD. Okay, I just divided this by GM square and then rewritten it like this. Okay, so we'll have GM square RD in the first term. Here I'll have 4 kT gamma by GM, right? This is GM square. So, and as we already know from our intuition, the noise current will not be required. But if you again go ahead and find it, we can do that also. So let's say this is noise voltage. So first of all, this noise voltage calculation, is it okay? Is it clear? Yeah, flicker noise. I mean, if flicker noise is also there, you can just add it along with it, right? That's all. So basically, whatever we do for the thermal noise, same thing will happen for flicker noise.
That is why we are not considering the noises of MOSFETs and
No, the idea is, see, we want to model this network by a noiseless network, right? We are supposed to find the input referred noise and voltage. Those will capture the noises generated in the actual network. Understand? So idea is simple. You take your network, you find what is the noise you get. In your model, you find what is the noise you get. Both of them have to be equal, and that's how we are finding this guy. Okay. Right. So let's so let's go ahead and find the current also. So for finding the current, what should I do to the source resistance? Infinite. So which means the input side is open. So I'll open this. So if I open this, I'll get some noise. Let's say we get something that is okay. So here I'll try to find the transfer function, and if I open this guy, the voltage source is kind of floating. It's not playing any role. So this is, let us say, not there, right? So now I am pumping in a current IN in. What is the gate voltage here? If I call it VG, what is VG, do you think? I mean, it's a current source pumping current into an open circuit. What is the voltage? I mean, okay, think of it like this. Current pumping into a R. Voltage is IR. For open circuit, what is that R? So what will that voltage be? VG is infinity. Similarly, you find the transfer function. What can you say about the transfer function? Transfer function will also be infinity, right? So which means you find some noise current here divided by infinity, it will become 0. Right? So that's why you don't have to worry about the noise current if your input impedance is infinity. Okay. Of course, in practice, you will have the gate parasitic capacitance. So the transfer function will not be exactly infinity. It will be frequency dependent, but let's say we ignore it. This is what we have. Basically, at low frequencies, you don't need the noise current to model the noise. Okay. Cool. So then let's look at second example. This okay? Yeah. So common source is done. So let's do common gate. So common gate, we have this. Gate is incrementally short. I apply the input here. Output is taken here. So once again we'll do the same thing. Let me draw the incremental circuit here. Input, and if we are trying to model the noise in this network by doing this. Sorry. This is what we are trying to do. So first here what is the input impedance, do you think? Yeah, let's all again assume R0 is infinity. So it's 1 by Gm. So you need both voltage and the current to model the total noise. Okay. So let's start with voltage. So for finding voltage, what will I do to Rs? 0. So which means the input side will be short. So here also the input side is short. Okay. So again I can try to find the short circuit current here. So I'll short the output in both places. So here, what do you think is the total noise current here? Let us say you model the noise due to resistor with a parallel current, noise due to the transistor with another parallel current. Say it's INRD and INM. With sum of the two, again it's same as what we had before. So I'll directly write S I out of F will be the two power spectral densities added. Okay. So here you have found the noise current. So here I just need to find the transfer function. So I have shorted the input. So what is the source voltage here? It's Vn in. So this voltage is Vn in. So which means what is the incremental current? Gm times Vn in. Okay. Again plus or minus, it doesn't matter. So the transfer function mod y is Gm. Is that okay? So once again, if you find the input referred noise, or if you're confused, we'll do that, right? So if you're confused, let's do compute the current here. See here, the noise current is only due to this noise voltage. So you'll have S I out of F to be the power spectral density of this guy times the magnitude squared of the transfer function from this input to this output, which as you know is Gm square. That's all. And you already know S I out of F, which is this. Equate the two and find it. So if I do that, I'll get the same thing as before. This will be 4 kT by Gm, 1 by Gm RD. Okay. Same thing, I'm dividing this by Gm square. Okay. No other change. Cool. So this is only the noise voltage. As you know, here the input impedance is not infinity. So you also have to find the noise current. So that also we can do quickly. So let me copy this. So here I am going to make Rs to be infinity. So which means the input side will be open. So this is basically open. Here also it's open. Okay. So now can you tell me what will be the total short circuit current here? That's one difference. Earlier this was grounded in the previous case. Now the source is open. So first of all, okay, that's confusing. Let's do one source at a time, superposition. So due to RD alone, what is the short circuit current? That directly flows to the output, no confusions. Let me copy this. So this is gone, so let me erase this. So I just need to then worry about this fellow, INM. So how much of this current do you think will flow to the output? Yeah, why? Remember, this side is open, so whatever current kind of comes here will flow back. So which means both these currents are equal. So here nothing will flow. Right? Second case here, the current flowing out will be the difference between the current entering in and the current flowing out. Both are same, so nothing will come. So SI out is simply, the output noise will be only due to the resistor. So if I find the SI out of F, it's 4 kT by. Okay. Yeah, so here then let's find it. Here this guy is open, so let me just open. So yeah, even if R0 is there, that's going to come in parallel to this.
That will flow through that R0.
Yeah. As of now I have not considered R0, so you can think of it as its current is circulating within a very high impedance. That's all. Yeah, practice, it's R0 is there, it will flow within R. Yeah. So we have found it here, so let's do the same thing in this model also. So if this is IN in, what is the output current? Same thing. Again, common gate is what do you use common gate for usually? Current buffer. So input current will be buffered at the output. So SI out of F will be SIN in of F times 1 square. So the transfer function is 1. So what is the input referred noise current per spectral density? It's the same thing as you computed earlier. That's all. Right? So hopefully now you get a feel for how this calculation is done. So let's take a few more. So let me take this guy. So this is where I apply the input. This is the output. Okay. Again, ignore R0. So first of all, here what is the input impedance? Infinite. So you don't need to find the current. Current will be 0 straight away. So only voltage is needed. So let me draw the incremental circuit here. So RD. So push some space. And in my model, so what should I do to the input? To find the voltage noise, I'll short the input. So again, I'll try to find the current. So can you find out and tell me? So please find out and tell me the noise contribution due to RD and RS. You'll have contribution due to 3 guys: RD, RS, and the transistor. So please find out and tell me what is I out due to the resistors alone. I'll wait for some time. I'll pause maybe. Let me resume it. Due to INS. So now you have INS. This is getting pumped into this node. You are supposed to find the current flowing here. So what do? Current division. This gets divided between RS and whatever impedance is there looking up. Looking up, what is the resistance? 1 by GM. Again, drain is short as well as R0 is infinity. So it's definitely 1 by GM. So this current will get split between these two guys, and what fraction of it will flow to the output. I mean, you need to find the current flowing here. What is that fraction? That's all. Okay. So if I simplify this, I'll get GMRS by 1 plus GMRS. Is that okay? See, noise correlations are very similar. I mean, it's straightforward. You just need to know the small signal impedances here and there. It is basically finding small signal gains from different currents, different voltages to some output. It's whatever you did in the first two mini quizzes, same thing. There's nothing different about this. You just need to know that this is a noise current, this has a path spectral density, so and so. If you know that, rest is all whatever you know before. Okay, so these two are done. We are still here to find the contribution due to the transistor. Let's do that. So I'll make some more space. Or maybe actually I'll make slightly. Let me draw the noise current source like this. Okay. So IN. Again, there are multiple ways in which you can find how much of this current flows to the output, but one neat trick is the following. So let us say I have, I'll use this, two nodes A and B, and I have a floating current source like this. See, the difficulty in finding the noise contribution from this is the fact that in the earlier cases, one of the terminals of the current source was grounded, so it was much easier. So now we have a floating current source. Both terminals are connected to two different nodes, so it is not very trivial, but of course you can easily find it. So let us say you have a case like this where a current source I is connected between two nodes like this, right? So if I split the two currents, if I split this current source as two identical current sources with the same current I, it is still fine, nothing changes. Okay, so let us say I have a case like this. What can you say about this node potential? I have two identical current sources, and what can you say anything about this node potential? It is not known. Again, it's the same CMFE problem. This can be anything in the world. It is not defined. If it can be anything in the world, what value you can choose it? You can make it 0. Nothing will change, right? So basically, then you can split this like this. A current source from A to ground. Yeah. Now if you see, as far as this node is concerned, I am required to pull out a current of I. That is done here. As far as the other node B is concerned, I should pump in the same current I into that node. Same thing is happening here. So this way you can split this floating current source into two grounded current sources, then it becomes easy to work out. Okay. This idea fine? And it's not the only way in which you can solve for this. You can as well find it in a normal way, but this makes it slightly simpler. Okay. So what we'll do is the following. But one thing you should be careful is the direction of the current sources. See, both the current sources should point in the same way, right? When you replace it, you can't make this current sources like this and other current source in the opposite direction. That's the only thing you should be careful. So I am going to take this floating current source, replace it by two grounded current sources. So what I am going to do is this. Okay. Fine. So both are INM and INM. So I have a current flowing. That's what I had before. I had a current that is flowing from this. Now I replace it by two current sources in appropriate direction. Is that okay? So now it's simple, very simple now. This current source will see the same thing as you had for the drain resistor RD. This current source will see the same effect as was happening for the current source associated with RS. So now it's relatively simple. So what is the current, what is the portion of this current flowing to the output? So we'll have INM directly flowing. Fine. For this guy, I'll basically flip it. To simplify it, I'll flip this direction and call it minus INM. Right. So here I'll have minus INM current flowing into the two resistors, I mean two impedances, RS and 1 by GM, the same impedance division, so we'll have the same thing. Okay. So you just have to be careful with the polarity here, that's all. Because if you flip the current polarity, everything gets messed up. If you are careful with this, then this is easy. So then you can simplify this. So if I simplify this, I'll have INM times 1 by 1 plus GMRS. Okay, this I have just simplified. So now I can directly write the path spectral density. So let me write it. SI out of F is 4 kT by RD plus 4 kT by RS times this transfer function square, plus for the transistor it's 4 kT gamma GM by 1 plus GM RS whole square. Okay. So this part is done. So now let's come to this guy. So the gate voltage is what? If I call the polarity as minus plus. Gate voltage is VNN. Now tell me what is the small signal short circuit current? What is IOUT, do you think? Yeah. How do you say that?
Because the source voltage, it's like a voltage source follower.
Yeah. So as he's saying, if I look at this voltage, it is like your source follower configuration. R0 is infinity. So what is the incremental voltage here? Times your VNN. Fine. So the voltage across the resistor is this. What is the current through the resistor? 1 by RS of that. That same current is what will flow. So the transfer function, if I just take the magnitude of the transfer function is so then you divide the two. Let me actually divide it just so that just want to make one point. So I'll divide it and write the full expression. So I'm going to divide it. This is VNN of F. Okay. This is what we are supposed to divide with. So the first term I'll write it directly, 4 kT by RD times something square. What happens to the second term? 4 kT? 4 kT times RS. Okay. What happens to the third term? 4 kT? Fine. So now let's stare at this guy, at least last two, and let's try to see if that makes sense. So what the second term says is the input referred noise due to the resistor RS is equal to its own voltage noise. So let's try to make sense of this quickly. So this is RS. I mean here I mean for calculation I had considered the noise to be modeled as a parallel current source, but I could also model it using a series voltage source like this, right? So now you know that, see, if this was not there, you will have current proportional to GM VGS. Now you are boosting this potential by Vn, so that the input side that's going to directly appear. So that is why you are getting 4 kT RS directly. And the second term, again, this is something you can, this term you can interpret like this. So if I have a MOSFET, I know that the drain current is modeled using 4 kT gamma GM. Now let us say, let me take to next page. So let us say I try to find the input referred noise for this transistor alone, right? Again, I'll ignore the gate capacitor. If I ignore the gate capacitor, to model the noise, I just require the voltage, right? And if I try to find the input referred noise voltage, what do you think that will be? Basically, you again do the same thing. You find the short circuit current. That will be 4 kT gamma. Let me write it. SVN of F is the output current is 4 kT gamma gm divided by the transfer function from the input voltage to the output current, which is gm square. So this is what you have. So again, I'll give you this exercise to prove it more formally. But if you have a case where you have a MOSFET like this, something is connected here, something is connected here, and if you ignore the gate capacitance, to model the noise, you can also model it using a series voltage source with a pass spectral density 4 kT gamma by gm. Okay. Again, I have not formally proven it. I have considered the source to be grounded, but you can also prove it otherwise. Again, I'll give it as an exercise so that you can convince yourself. So as long as you don't consider the gate capacitance, you can do this. Okay. Cool. So one more last circuit we'll do today. So that will be our dear Cascode. So Cascode, here is where I apply the input, and let's assume that the output side I have an ideal current source. Okay, don't worry about what's here. Assume that this is an ideal current source. We don't have to worry. This is the output. This is incrementally short or connected to a bias voltage. So again, let's start with finding the short circuit noise current. So incrementally this is open. I'll find the short circuit noise current. This is shorted. Again, for finding the voltage, again the input is applied to the gate. Input impedance is infinity because gate cap is not considered. So only voltage is required, and for finding the voltage, I'm shorting the input. Okay. So again, VB is incrementally short. So again, there are different ways in which you can do. Like I told, you can model the noise current. Noise like a parallel current source or a series voltage source at the gate. So what we'll do is we'll try to do it the second way, like a series voltage source. So if I model this as a series voltage source, fine, the input referred noise voltage due to this transistor is directly its own input referred noise. Fine. Is that okay? So if I find the Vn in, due to the transistor, let us say M1, that will be basically directly 4 kT gamma by gm. Right? So that is done. Next is for this transistor. So now I will not consider this. Again, for this transistor, we can either model the noise as a voltage source here or a current source here. So let's actually start with current source and then do the same thing with the voltage source and see how it's going to behave. So let us say it's IN2. So now we have a similar case. The current source is kind of floating, connected between two nodes. We can do it the same way. I'll do this. Again, let's consider R0 to be infinity to begin with. So this is incrementally short. So this current source, yeah, this is okay. Okay. So now if you first ignore R0 for all transistors, let's see what happens to I out. So how much of IN2 will flow to I out? The entire thing will flow. So if I write I out will be IN2, that is due to this guy. Similarly due to this guy. So I'll have, let us say, I'll change the current direction. The current flowing here is minus IN2. Okay. So now this current again sees two impedances. Looking down, what is the impedance? Infinite. R0 is infinity. So all the current will flow up. That is basically 1 by Gm. So the entire current minus IN2 will flow. So what is the total current? 0. Okay. So that is one nice thing about Cascode. So whatever transistor you are adding for boosting the output resistance, that is boosting the output resistance, yes, but it is not contributing to excess noise. So that is one nice thing about Cascode. Okay. And see, here the current is exactly 0 because we have ignored the output resistance of all transistors, right? So let's quickly consider the output resistance and see how much it actually reduces it by. So that we'll do that and wrap up today. So let's consider R0 now. Let's do that quickly and finish it. If I consider R0, again I'll have two two current sources, this guy. So how much of IN2 will flow to the I out if I include R0? Entire thing will flow, that is directly connected to the short circuit. So this guy is fine. So only the second current source. So here I have minus IN2. So that divides between R0 of transistor M1 and what is the impedance looking up? 1 by Gm2. So what fraction of the current will flow to the output? It's going to be times R01 by R01 plus 1 by Gm2, right? So let me put it here. If I simplify this, I'll have IN2 minus IN2 times Gm2 by, so this is going to be IN2 times 1 by 1 plus. So even if R0 is there, as long as the R0 is large enough, the current gets suppressed by this factor. Okay. So again, if I were to write the total thingy, so let me write it. So this is basically the short circuit current. Now if I find the transfer function from the input voltage to the output current, what is that? If I apply Vn in here, we have to find the transfer function from Vn in to the output noise current. What is that? Gm. So to find the input referred noise due to the second transistor, I know the current. I have to divide it by Gm1, right? So here this will be 4 kt gamma Gm2 by 1 plus Gm2 R01 whole square. So basically written this pass spectral density 4 kt gamma Gm2 by the transfer function we got squared, that is the output current noise PSD, divided by the transfer function square. Okay. So again take it as an exercise and repeat the same thing by considering the noise as a voltage source here. Okay, so what I'm saying is, so let me clean it up. Find the noise contribution due to M2 by modeling the noise due to M2 as a voltage here. So you have, I think here you find how much of it comes to the output and refer it back to this input. That's all. So this you do it so that you get a. So I'll stop here. Yeah.
Answer will come same.
Sorry?
Answer will come same.
Should come same, right? I mean, so that's, you know the answer, you just